In this video, we start discussing the spectrum of bounded linear operators between Banach spaces. We've done that already in the case of Hilbert spaces, and of course a lot of the definitions are exactly the same when we move to Banach spaces. The definition of the null space stays as it was, just a set of vectors that are sent to zero. The definition of the resolvent set stays the same, it's just a set of those lambdas for which lambda minus t is a bijection, and now we know from the open mapping theorem that the inverse will have to be a bounded linear map. The spectrum is just the complement of the resolvent set, and the set of eigenvalues are the set of those lambdas for which the null space of lambda minus t is non-trivial. The concept we're going to add to this bunch of definition is the concept of approximate point spectrum. So the approximate point spectrum is a part of the spectrum that contains the eigenvalue but can be larger than the set of eigenvalues. These are those lambdas for which you can find maybe not an eigenvector, but a sequence of approximate eigenvectors. So elements of the unit sphere that are sent to zero, as you take a limit, by lambda minus t. Now that has to be in the spectrum, because if lambda were to be in the resolvent set, then lambda minus t would be invertible. You could apply lambda minus t inverse to this to get xn back, and this would have to go to zero, which is impossible if the xn stay on the unit sphere. So this is clearly a part of the spectrum. This may not be all of the spectrum. This clearly contains the eigenvalues, because you can take a sequence that's constant equal to the eigenvector, but a priori all these inclusions are strict. Now we're going to prove a proposition in this short video, and this proposition will describe what lambdas that are not in the approximate point spectrum look like. So if you have a lambda that is not in the approximate point spectrum, well, for sure it cannot be an eigenvalue, so the null space would have to be trivial, and it may be that it's a lambda in the resolvent set, and so the range is the entire space. And if it's not the entire space, so if you are genuinely in the spectrum but not in the approximate point spectrum, then you need a trivial null space and a closed range. And that characterizes those lambda not in the approximate point spectrum. That's property 3. And then we also have property 2, which tells you, not that lambda minus t can be inverted, but that lambda minus t of x is greater than some multiple of the norm of x, right? So in particular, this condition here cannot happen, and of course the null space cannot be trivial. So we're going to prove that these three things are exactly equivalent. Okay, so let's start with 1 implied 2 and assume that 2 doesn't hold, and then we'll prove that 1 doesn't hold. So we assume that for every c there exists an x in x such that lambda x minus t of x is strictly smaller than c times norm of x. Now notice that if that holds, then c cannot be 0, because if not we would get, x cannot be 0, because if x were to be 0, we would have 0 strictly smaller than 0. Now if that's true for every c, I can take c to be of the form 1 upon n, so I get that for every n in n there exists an xn in x that is non-zero, such that lambda xn minus t xn is smaller than 1 upon n times norm of xn. Now my xn is non-zero, so I can divide by norm of xn on both sides, and what do I get? I get that there exists a sequence yn in the unit sphere, because these are the xn divided by their norm, such that lambda yn minus t yn, well, it's always smaller than 1 upon n for all n, so in particular this goes to 0. And that is exactly saying that lambda is not in the in the approximate point spectrum. Okay, so we've proven 1 implies 2. Now what about 2 implies 3? Okay, so we have to prove that the kernel is trivial and that the range is closed. Let's start with an x in the kernel, in the null space of lambda minus t. And if I have such an x, then lambda x minus tx, well, it has to be 0, because x is in the null space of lambda minus t, and in the meantime it has to be greater than a constant times x by 2, and therefore x has to be 0. So the null space does have to be trivial. And now for the range, what can I say about the range? I take a sequence xn in x that is such that lambda xn minus txn converges to something. Let's call y the limit. And now I have to show that y is actually in the range. Okay, so how do I do this? I look at xn minus xm. I want to show that xn actually is a Cauchy sequence. This has to be smaller than 1 upon c times lambda xn minus txn xn minus xm txn minus xm. Right. But this is a Cauchy sequence because lambda xn minus txn does converge to y. So therefore there exists an x in x such that xn converges to x as n goes to infinity. Very good. But then lambda minus t is a bounded operator. So lambda xn minus txn has to converge to t of x. So lambda xn minus lambda x minus t of x has to go to 0. And that gives y equal lambda x minus t of x by uniqueness of the limit. So the range of lambda minus t has to be closed. Right, that proves 2 implies 3. Now we have one more thing to do. I just prove that 3 implies 1. So I start with 3, my range is closed, and so it is a Banach space. It's a closed subspace of a Banach space. So now I can look at the operator lambda minus t as a map from x to its range, and I have that the kernel of lambda minus t, the null space of lambda minus t is trivial. So lambda minus t is a bijection from x to the range, because you're obviously surjective onto your range. And so by the open mapping theorem, I get that there is an inverse lambda minus t that is a bounded linear map from the range of lambda minus t back to x. Okay, now assume by contradiction that the lambda is in the approximate point spectrum of t, and so there exists a sequence xn in the unit sphere of x that is such that lambda xn minus txn goes to 0. Right. Now that sequence lambda xn minus txn is certainly in the range. So you can apply the inverse to that, and what you get is that xn, the norm of xn, which is 1, has to be equal to lambda minus t minus 1, seen as a bounded operator from the range back to x, applied to lambda minus t applied to xn. Okay, but that is smaller than the norm of lambda minus t minus 1 times the norm of lambda minus txn, and lambda minus txn goes to 0. And so we get a contradiction. And that concludes the proof of this little proposition and this very short video that just described approximate point spectrum for bounded linear operators between Banach spaces.